Oh, and I didn't check if that was no. Yeah, okay. There we go. Oh, I forgot to change the title of this one. Let's fix that. So note all that. All right, so today we're talking about Bernoulli equations. You have one section and some examples. So it'll be relatively short today. I don't know if we'll finish before the end of class, but hopefully we do, so I can give you back your homeworks. And you can get to your next class or go home. But let's get started with what we're actually looking at. So a Bernoulli differential equation is one that you can write this way. It looks very, very similar to a linear equation, only it's not linear because of what makes it not linear here. Yeah, the y to the r power. So it could be linear if r is equal to 0 and q is not 0. And if r is equal to 1, we get back a separable equation because we can pull that y to the r to the other side and then factor it out when r is equal to 1. And then we just have p minus q as the coefficient. But if r is not 1, then we have a nonlinear equation, and we don't know how to solve many of those yet unless they're separable. So here's one example of a class of differential equations that is not linear, which we can find a solution method for. But first, let's get a little bit of practice with recognizing Bernoulli dEs. So I'll give you a couple of minutes for this one. Let's say we go until 4:07. Give that a shot. See if you can figure out what the value of r is for each one of these equations. You may have to rearrange some of them.
It's gonna be 1/6 Yes. Oh, that is how. Yeah. T to the y. That's all. It's 1/3, so there's 1/3. I think it's 1/6.
All right, so let's give this one a shot. Anyone have an answer for the first one, top left? 2? Okay, yes. So right here, this is in standard form already for a Bernoulli DE. We have the derivative here plus some function of x times y. Okay, so this is your p. This is your q right here, also x. And then y to the r. So we'll circle that and say that is r. All right. And then maybe we'll also label p and q just for kicks. Okay. So what about that top right one? -3. Yeah. So we have to rearrange this a little bit. We have dx dt, and then this part right here is the linear part. We have x as the dependent variable, t is the independent, and so we want this part to be p times x, and then this part is left over, so that goes to the other side, and we have plus 1 over t x equals minus t x to the -3. And then there's our value of r. And again, there's our q, this time of t, and p of t. Okay. What about that bottom left one? 1/6, good. So it's not written clearly there. Everything is in the form it should be, except for the r now. So this is y to the 1/2 to the 1/3. And then using properties of exponents, you can multiply those two and you get y to the 1/6. So there's our value of r, 1/6. Notice that that is not an integer, and that's okay. Bernoulli DEs don't care whether the exponent there is an integer or not, because the solution method that we'll find for them, the type of number that r is irrelevant. All right, what about that last one? Also 2. So it might look a little weird here with that theta out front, but we can divide by that and note that it's also the independent variable. So that 3 doesn't affect the standard form of the Bernoulli DE. So if we rewrite this, we have dr d theta equals, not equals, sorry, plus 2 over theta squared r equals, and again, that's not plus, that's minus. Can't do algebra today. Equals 1 over theta cubed r squared. There's our value of r, which is again equal to 2. So that's a little bit of practice, just recognizing these, putting them into standard form, seeing what the parameter is. And how about a solution method? How do we do this? Well, if you have a Bernoulli equation, like the ones we saw a second ago, then you can apply this change of variables. We've been doing lots of substitutions. And this change of variables will turn it into a linear equation. And those are the ones that we solve using integrating factors. So let's just see how that works. How do we get a linear equation out of a Bernoulli? So first off, we need dy dx plus P y equals Q y to the R power. Okay. And then if we have this substitution, V equal y to the 1 minus R, how do we transform our DEs? Usually we want to find V in terms of y and dy dx in terms of V, or sorry, y in terms of V and then dy dx in terms of V. I'll go back to the, or I'll write it down here. It's, oh, I already did. It's a differential equation that looks like this, where you have y to some power on the other side. Okay, so what we want to do now is make our substitution. We can solve for y if we want, and then take a derivative. That might be a little annoying. I'm not sure which one is going to be easier, actually. So let's try it the way it is for now. dv dx equals 1 minus r y to the minus r, 1 minus r minus 1. It's just the power rule there. All right, so there's our dv dx. And then we have y equals v to the, where are we here? 1 over 1 minus r. Okay, so if we put that in here, we have 1 minus r, y to the minus r. We can do that over here, actually. It's v to the r over r minus 1. So that's what I want to put over there. V to the r over r minus 1. And what did I do? We have dv dx in terms of this thing, and then, oh, I forgot a term. Sorry about that. I want my y prime here. There we go. Okay. So now we've got our y prime here, and maybe we add on py. So dv dx plus py here is going to be equal to, no, that's not what I want. Sorry, brain's a little scattered today. Let's take this one, solve it for dy dx, and then we'll plug things in. Okay. dv dx equals 1 minus r. Y is v to the r over r minus 1. And then dy dx is q, also y to the r. So r minus r over r minus 1. And this is p times v to the 1 over 1 minus r. Okay, so that looks kind of ugly, except if we multiply everything out here, we should get something a little bit easier. I'm doing something wrong. Okay. I'm not remembering how to do this, so we'll come back to that at the end of class if I can remember. I can at least tell you where the substitution comes from, and that will be easier. What the heck? I don't know why I did that. Technical difficulties, sorry. Why did we do that? Okay, all right. We're back, sorry about that. So where does this substitution come from? That part I can at least tell you. So if we start with our Bernoulli equation here, dy dx equals p, or plus py equals q y to the r power. Well, I like linear equations. I like separable ones too. And it would be really nice if that y to the r wasn't there. If it wasn't, then I would have a linear equation. So what happens if I just divide it out? Well, I have to divide it on the other side. So what does that give me? Well, now I have 1 over, let's write it as y to the minus r dy dx plus p times y to the 1 minus r equals q. And that y to the 1 minus r is sort of a hint that something should happen with 1 minus r over on the derivative side as well. So if we take a look at this derivative, well, what does that look like? That looks like the derivative of y to the 1 minus r. Except it's missing a little bit of stuff. All right, so it looks like the result of a chain rule, implicit differentiation, something like that. If I take the derivative of this, what do I get? 1 minus r y to the minus r dy dx. Oh, okay. So this is the factor that's missing here, is that 1 minus r in front. Well, I can go ahead and insert that. 1 minus r over 1 minus r. And then I have that the upper part gets absorbed in. And so this is equal to 1 over 1 minus r times d dx of y to the 1 minus r. And so if I put that into my differential equation now, well, okay, I'm almost there because I only see this part, right? Oh wait, but I inserted the 1 minus r's. So those go in as well. And this whole thing is equal to 1 over 1 minus r d dx of y to the 1 minus r plus p times y to the 1 minus r equals q. And so now you have the same function of y in both the derivative and y itself. And actually, this will serve as a proof that it is linear. So if this is v, then we end up with the equation 1 over 1 minus r dv dx plus p times v equals q. And writing it in standard form for a linear equation, we just have this extra factor of 1 minus r on both p and q. And so now this is a linear equation. We know how to solve it using integrating factors, and we can get a solution. At the end of that solution, we'll have to substitute back in for y, but we can do it. All right. And after that, we want to get some examples out of the way. So I'll do this one, and then I'll give you a couple of examples. You need to go back. So I'll do that one, and then I'll give you a couple of examples afterwards to work on, and then that's all we have for today. All right. You ready? All right. So to start this one, we want to make sure that we identify everything, right? So we need P and Q. So there's P, there's Q, and now we have R is 3. And, you know, I know we could go back and use the formula we just found as a shortcut, but let's go ahead and do it directly so we see how things work. So we want v equals y to the 1 minus r is 3. So v is y to the minus 2. All right. So now I need dy dx. So I'll take a derivative of both sides here. And I'll get minus 2y to the minus 3 dy dx. Okay. And then, again, we did things one way a second ago. Here's another way that we can do them that works a little bit better when you're computing these directly. Multiply both sides of this equation by the thing that you see over here. So multiply by minus 2y to the minus 3 dy dx minus, okay, minus 2y to the minus 3 times 5y equals minus 2y to the minus 3 times minus 5 halves x y to the third. All right, see how those exponents cancel out real nice? That's how this substitution works, is it essentially gets rid of the nastiness on this side when you multiply through by that thing. It's the same as the dividing out by y cubed that we saw a second ago. So going through and substituting, that's dv dx. We see that over there. And so we have dv dx minus minus plus 10, and then y to the 1 and y to the minus 3 gives us y to the minus 2, yep. And then on the other side, we have that cancellation in the exponents. So we get positive 5x, and that's it. 2's cancel out, negatives cancel out, and then the y to the third cancels out with y to the minus third. Okay. And very last thing is that we didn't need to write y to the minus 2 there because that's v. So our differential equation is dv dx plus 10v equals 5x, which is linear in v. So we had a nonlinear equation to start. We were able to transform it into a linear one in a different variable. All right, let's go ahead and finish solving this one. Get a little bit more practice with our integrating factors. 10v equals 5x. Okay, so I need my integrating factor. How do I get that? Yep. So e to the integral, and then p is just 10 here, right? And this is q. So we have a new p and a new q.
You said, so Bernoulli takes a nonlinear function to a linear function.
A nonlinear equation to a linear equation.
So that's the whole point.
Yeah, it's the whole point of this substitution. Is it takes this particular type of nonlinear equation, turns it into an easy one that we know how to solve. All right, so we have this, and then that gives us e to the 10x power as our integrating factor. All right, go ahead and multiply through by it. E to the 10x dv dx plus 10 e to the 10x. Okay, that makes sense. Equals 5x e to the 10x. All right, on the left side, that's a product rule of e to the 10x and v. And on the right side, we're going to go ahead and integrate. How do I integrate this? What's my trick for integrating the right side? It's one of those three that we covered at the beginning of class, or of the course. Louder? It's okay. You're wrong, you're wrong. If you're right, you're right. Not U sub. Sorry? Chain rule? Not the chain rule, but the integral form of a different one. There's three techniques we covered. They were U sub, integration by parts, and no, that last integration technique. Okay, let's go back over those real quick. Three main integration techniques: U sub, 2, integration by parts, 3, last one, partial fractions. There we go. Partial fraction decomposition. I know there's a lot in Calc 2, but these are the three main ones that are useful in this class. So I want you to know those ones at least. All right. So now remind me, which one is going to be useful for this integral? Integration by parts. Yes. Yeah. Why is that the one we want to choose here? Yes. You have this times this, and one of them will go away if you differentiate it. Okay. So let's do that. On the left side, e to the 10x times v. On the right side, we need our integration by parts formula. Let's do it explicitly here. What's u? 5x, the thing that we're going to differentiate out. All right, so du is 5 dx. That leaves what for dv? E to the 10x dx. Don't forget that part. All right, what's the antiderivative of this? Yeah, 1/10 of it. All right. And then our integration by parts formula says do this positive, this negative. And so we have 5/10. So 1/2 x e to the 10x for that first term, that partially integrated term, minus antiderivative of v du. So we have also 1/2 e to the 10x dx. All right, and then we go ahead and integrate that. And we get 1/20 e to the 10x plus c. All right. So last thing is we want to solve for y, right? So now we've essentially got an equation that defines y or v in terms of x. V equals 1/2 x minus 1/20 plus c e to the minus 10x, because the e to the 10x is cancel except for the c part. And then v was our substitution, y to the 1 minus 3 or minus 2. All right. And then sometimes I like to write that a little more simply as 1/y squared, because it makes it easier for me to do the algebra to solve for y. And we have y squared equals 1/, all of this stuff, plus c e to the minus 10x. Okay. If you want to simplify that a little bit more, get rid of complex fractions, we can multiply through by 20 on top and bottom. And we'll get 10x minus 1 plus c e to the minus 10x. Okay. And then if you were given an initial value, you could plug it in here, or you could take the square root and make sure to account for the plus minus. But this is all we needed for this example, is just find a general solution. Okay, questions about this example? Yeah. If you get to here, it's fine. It's just a little easier to read if you write this down. And that's what I will have in the key.
Why are we leaving it as 5 squared for the right front?
Because it's an equation that's relatively simple, and if I take square roots of things, I have to account for it with a plus minus, which is kind of annoying.
Okay.
But other than that, no reason. Okay. This one's yours. So don't forget to classify it at the beginning. It's Bernoulli, of course, but find P, find Q, find R, and then solve it. It'll give you a hint. You can just use the formulas we've already derived. That's perfectly fine, so you don't have to redo the work. Unless I say so. It has not. Does it have the attendance sheet?
Yeah, I agree with
Sorry, I always come late. But it must take like.
Is there anybody else that still needs the attendance sheet?
Is it graded? Like, is it like, it affects your grade? Oh.
It says like. Yeah. Okay. You only get 20 minutes.
Yeah. Not too bad. My presentation is either. So it's kind of a, it'll laugh at something. So it's great. Oh, you chose.
Yes. It's just annoying. The time is just. Oh, wait. 4:45. You're going tomorrow. We can get the thing. This is the one. I'm repping Charlotte. Oh no, there's like a. I'm going. Tall one. I know we're gonna. Oh, wait. Oh, you get it. Oh, I'm sorry. Oh, that makes sense. Yes. Like people with science versus I know. Like they were added to it was it's like there's no way yeah, I mean, it's kind of big, but it's only like 1,200 kids. My graduating class is about 5.
All right, seems like we've gone through most of it. So let's do it together. Why don't you guys classify this for me? What's, how do I rewrite it, and what's my value of R? R is -1. A 4 does show up. So we get dy dx, and then I'm looking for the term with a y to the 1 power. Anything else is the stuff that goes on the other side of the equality. So let's bring this over here. We have -2 over x times y. So when I'm writing things in standard form, I always want to separate the y part off there. And this is equal to minus x squared and then y to the -1. And that's how I find my value of r. Okay. So there's r. It's -1. And standard form for Bernoulli tells me that actually it's blue. That's p of x, blue. And that's q of x. Okay. And so now we'll do this the long way one more time, and then the last one we'll use the formula for. So we have v equals y to the 1 minus -1. So r was -1, and the formula is 1 minus r. And that gives us y squared. That's nicer to take a derivative of, so leave it like that. And if we differentiate that equation now that defines our change of variables, we get 2y dy dx. All right, and then this tells us how to change our equation. So we want to multiply everything by 2y on both sides to get dv dx to show up. Do that one more time. 2y times dy dx, and then minus 2y times 2 over x times y equals minus 2y and then times x squared y to the minus 1. Right, so now once more we get our cancellation, and we have to make sure that we do all of our substitutions. This part is dv dx. That y and that y together are going to give us v, and then these just cancel out, and then the rest of the stuff in our differential equation is that way. There we go. Minus 4 over x, 2 times 2 there, equals minus 2x squared. All right, there's our linear equation. Okay, and we'll rewrite that here. dv dx minus 4 over x, v equals minus 2x squared. And now we want to find our integrating factor. So we have a new p, maybe we'll use capital P here, and a new q, and our integrating factor should be e to the integral minus 4 over x. So that p of x coefficient. If we go through and do that, we should get 1 over x to the 4th power. Yep. And if we multiply through by that, we get 1 over x to the 4th dv dx minus 4 over x to the 5th v equals minus 2 over x squared. Then we go ahead and undo our product rule here. Equals this antiderivative x squared dx. These cancel out. So we have v over x to the 4th power equals, antiderivative of that should be power rule. We got minus 2x to the minus 2. We take an antiderivative. Yes, just 2 over x. This is 2x to the minus 1 over minus 1. Just 2 over x. Okay, so we get 2 over x plus c there. All right, last part, multiply by that x to the 4th and substitute for y. Question?
So when I inverted,
Yes, so I skipped some steps there. You should get e to the minus 4 log x. And then using log rules, that gives you log x to the minus 4th power, minus 4. Yeah, and then those cancel out. Okay. So, all right, so this is y squared over x to the fourth. Solve for y squared, and we get 2x cubed plus cx to the fourth power. And if you want, y equal plus minus square root of 2x cubed plus cx to the fourth. Either of those is fine. Minus 4 over x to the fifth. That's part of the product rule. So this whole thing is this derivative here. So this is the derivative of v times 1 over x to the fourth. This is the derivative of 1 over x to the fourth times v, and then you add them together. And then, yeah, and then you undo it with the antiderivative. All right, so there's our solution. That's it. Okay. And there was another question.
No, I said like.
Okay. Any other ones? Finish this last one, and then you'll be free to go. Oh, because I used my substitution to go backwards. So this v right here, I remember that v was y to the 1 minus r, which ended up being y squared for me. Okay. So we have one last example, which I meant to put at the top of the page. Let's try to use our formula for this one. So our formula, once we went through and put all the Bernoulli stuff in, we should get this differential equation. 1 minus r p times v equals 1 minus r q. Okay. And so all we have to do if we know this is then find our integrating factor and write down the solution. So let's see, our integrating factor in this case would be e to the antiderivative 1 minus r p of x dx. Okay. It saves us a little bit of work. So here, immediately, once I know p, see that up here. So p of x and q of x. All right. So immediately we can write down our new differential equation. And then I forgot to tell you r. R is 2 right there. So we get dv dx plus 1 minus 2 is -1 times 1 over x times v equals -1 times x squared. So we didn't have to go through all that change of variable stuff. We just have the formula right there, and we get this differential equation immediately. Okay. Our mu of x then is integral of all that stuff, or e to the integral -1 times p is 1 over x, or e to the minus log x, which is 1 over x. Okay. So we want to multiply everything by 1 over x here. Or we can recognize that that's going to immediately give us the product rule. Equals -1 times x, or just x. And now we integrate both sides. do that on the next page. So we have d dx 1 over xb equals minus x. Integrate both sides, and we get 1 over xb equals minus 1/2 x squared plus c. V was, I didn't even tell you what V was it? Did I? We had R was 2, V would be y to the 1 minus 2, okay, 1 over y. So we have 1 over x times y equals minus 1/2 x squared plus c. And we can just swap all of this with y. So we have 1 over x times minus 1/2 x squared plus c equals y. All right, and multiply top and bottom by 2. We get 2 over minus x cubed plus cx. Another way of writing the solution without fractions. All right, so a little bit less work if you just know the formula there. You know that you just have to change the integrating factor for a Bernoulli to this. You insert that 1 minus r factor, and that gives you an answer right away using this formula. Okay, that's all I've got for you today. Make sure that you come up and get your homework. We got a little bit of time.